Hello students, I am Dr. Karim Sheikh and this video is for Sem-V students. The paper number is P304 and that is analytical chemistry. And today's topic is IR spectroscopy. This is the first lecture. Okay, now in first lecture we will discuss what is IR spectroscopy and explain the molecular vibrations in AB2 types of molecule. Okay, now first, IR spectroscopy is also known as infrared spectroscopy. It is one of the important spectroscopics for the assignment of the structure of unknown compound. Okay, now all the compounds having covalent bond, whether organic or inorganic, they absorb various frequencies of electromagnetic radiation in the infrared region. Electromagnetic radiation is made up of different types of region. The absorption of infrared radiation can be expressed either in terms of wavelength, that is lambda, or in wave number, here nu bar. Okay. In terms of wavelength, the IR region lies between 2.5 micrometer to 25 micrometer, and 1 micrometer is equal to 10 raised to minus 6 centimeter, and 1 nanometer is equal to 10 raised to minus 9 centimeter. Okay. Now the IR spectroscopy, it is divided into the region. That region lies between 200 to 14,000 centimeter inverse. That means divided into three different categories or three different regions: far IR, IR and near IR. Okay, now the relationship between wavelength and wave number is as follows. As we know that wave number is inversely proportional to wavelength. The unit of wave number is centimeter inverse. Now the IR plot or IR graph is percentage transmission versus wave number. Here we observe the IR spectra in form of band. For example, it is our organic molecule in which we have carbonyl functional group, that is C double bond O. So if we get the band at the region 17-16 centimeter inverse, that shows the carbonyl group is present in our organic compound. Now molecular vibrations. When infrared light is passed through the sample, the vibration and rotational energies of molecules are increased. So we get two types of molecular vibration. First, that is stretching, and second, that is bending vibration. In case of stretching vibration, there is increase or decrease in bond length between two atoms. It's called stretching process, and vibration arises due to this process is known as stretching vibration. Means in case of stretching vibration, there is change in bond length. Bond angle remains the same. Okay, now again stretching vibration is further divided into two types. First, symmetrical stretching, and second, asymmetrical stretching. In case of symmetrical stretching, the it is AB2 type of molecule. So we can take example of water molecule H2O, CO2 molecule, SO2 molecule, etc. So here the same B molecule stretch the vibration to opposite direction to each other, that is symmetrical stretching. In case of asymmetrical stretching, all the atoms stretch the vibration to one side, either one side. Okay, that it generates asymmetrical stretching. Now bending vibration. Bending vibration arises due to change in change in bond angle with respect to common atom. In case of stretching vibration, there is change in bond length, and here change in bond angle. Now bending vibrations are further divided into four types, that is scissoring, rocking, wagging and twisting. Scissoring means scissor-like motion. Bonds come close to each other or away to each other simultaneously, thereby change in angle. Okay, now that is second, rocking, bending. Rocking means both the atoms move on the same direction, or motion of both bonds in the same direction. Now wagging. Wagging vibration arises due to out of the plane. With respect to central atom, both atoms move behind or above the plane simultaneously. In case of twisting vibration, with respect to central atom, one atom move behind and another atom moves above the plane, means like a twist. That is twist in rotation or twist in bending. Now, how we describe whether how we get fundamental vibration for linear molecules and for non-linear molecules. Okay. In case of non-linear molecules, we get fundamental vibrations 3n minus 6, and for linear molecule fundamental vibration 3n minus 5, where n is number of atoms. We are taking one example, that is CO2. CO2. First, we should know the structure of our molecule, right? CO2 is linear molecule. So we are going to use the fundamental vibration for linear molecules, and that is 3n minus 5. Okay. CO2 is the linear molecule. Therefore, the vibrations 3n minus 5, where n stands for number of atoms. So here we have 3 atoms. So n is equal to 3, and we get 4 fundamental vibrations for CO2 molecule. Now, what is the requirement for IR active transitions? So it is very important that only those vibrations that result in change in dipole moment of molecule are absorbed in IR. That means if the molecule possesses dipole moment, then it shows IR active. They become IR active. Dipole moment means separation of charge. For example, water molecule, it has separation of charge, H plus OH minus. Okay. Now, okay, which four vibrations are possible in CO2 molecules? So, first, that is CO2 shows symmetrical stretching in CO2. Okay, now due to symmetrical stretching, there is no generation of dipole moment, right? So, it does not possess dipole moment. Therefore, it is IR inactive. In case of asymmetrical stretching in CO2, which having dipole moment, so it become IR active, and it shows bend at 2350 centimeter inverse. Now, 2 more bending vibrations. Total 4 vibrations are possible in case of CO2 linear molecule. So, remaining 2 more bonding vibrations, scissoring bending and doubly degenerated appear as peak at 666 centimeter inverse due to equal in energy. Now, scissoring motion doubly degenerated at 666 centimeter inverse. Okay. In next video, we will discuss further. Thank you.